Welcome, ladies and gentlemen. This is video number 4 in our equilibrium unit. This is the video on common ions. So what I'm going to be discussing in this video are basically what if we're in the situation where we are not starting with zero product. Actually, that's a common ion type of problem. And we're going to be making lists of ions that we have in solution. We are going to be seeing ice charts again. They absolutely were going to pop up again in equilibrium. And then I'm going to end with talking about how we can do a common ion problem with Ka, Kb, or Ksp, and I'll be doing an example common ion problem as well. With common ions, we're moving into the secondary topics of equilibrium. So we're moving past our primary topics, which are the most important skills, and into secondary. Now, with secondary topics, we have to remember all of our primary topic skills. You will still be writing equilibrium expressions. You may be calculating K from concentration, and you will definitely be calculating concentration from K. So we have to retain all of those skills, and we're basically going to start to add on and look at some more intricacies of equilibrium problems. So, common ions. The common ion effect is defined as a shift in equilibrium position due to the addition of an ion that's already involved in the equilibrium reaction. Essentially, this is Le Chatelier. This is Le Chatelier with an equilibrium system. And I know we haven't covered Le Chatelier yet, but you might remember Le Chatelier's principle from Regents Chem. So it's the same. It's absolutely the same idea. So this example problem right here says consider the addition of ammonium chloride to 1 molar ammonia solution. Now, ammonium chloride, NH4Cl, this is soluble, so it 100% dissociates. So when you put ammonium chloride in an aqueous solution, you get this process happening 100%. Which means that you don't really have NH4Cl anymore. What you really have is a whole bunch of NH4 plus and Cl minus ions, right? Ammonium chloride is a soluble salt. It 100% dissociates into its ions. So you really have a lot of ammonium and chloride solution. Now we're putting this, what are we putting this in? We're not just putting this in water, we're putting this in a 1 molar ammonia solution. So let's consider that process right here. Now, this reaction shown here, this is the ammonia-base dissociation reaction. This reaction was already happening, right? This reaction was already occurring because you had ammonia in solution. So, okay, it's going to be a base and it's going to dissociate like a base does. Then you add in a whole bunch of ammonium chloride, and notice that ammonium that we have right here is also right here in the equilibrium reaction that was already occurring in solution. So we just added more. We added a whole lot more of ammonium. And by adding more product, which is what we did, we caused a shift left in the equilibrium position. Because suddenly, you add too much product, you might remember that means that you're going to have to shift to the left in order to create more reactant. Well, what that's going to mean is this point right here, that the amount of hydroxide we have is actually going to go down because we're going to have to shift away from the hydroxide. By adding that product, that NH4 plus, that common ion to the equilibrium reaction that was already occurring, we've actually shifted away from the products and more towards the reactants. Now, the common ion effect, putting it another way, with this exact same idea, if you have a compound plus its soluble salt that generates a common ion, remember, weak acids do not react with their conjugate bases, which is sort of what we saw in the previous slide, is NH3 does actually not react with NH4 plus, right? They're conjugates of one another. It causes, this is the big point, that left shift towards the reactants cuts down on the percent ionization of your compound, and it could be the percent ionization of your acid, it could be the percent dissociation of your base, it could be the percent dissociation of a KSP, of an insoluble salt. Having an ion that's already part of the equilibrium reaction, that's actually already a product there, will push everything back towards the reactant side and really cut down on that percent ionization of that reactant. So having something there that's already a product, that's already a part of the equilibrium, that's called the common ion effect, and it cuts down on how much your acid, your base, or your insoluble salt can dissociate. And really, it's down to this explanation right here. Why does it do that? Why does it shift left, even if we haven't really talked about Le Chatelier yet? It's because the K value is a constant, and the K value is a ratio of products to reactants. Products are on top, reactants are on bottom. And if you suddenly increase your amount of product, you have to get the ratio back. K has to be the same value all of the time. So if you make one of your reactants really, really big very suddenly by adding more of it into the equilibrium process, then the other reactant, I'm sorry, if you make one of the products really big, then the other product is going to have to get really, really, really small, or your reactants are going to have to get bigger in order to compensate. You have to get that ratio back. K is a ratio, and for a given reaction, it's the same ratio at the same temperature all of the time, which means that you can have different amounts of your reactants and products, but the ratio of them has to be the same. So if you have two products and suddenly you make one product really, really, really big in terms of concentration, then the other one will have to get really, really, really small in order to compensate for that common ion. So common ion effect problems. How do you do a common ion effect problem? Realistically, the nice thing is you do it exactly the same way you do any other equilibrium problem. You just kind of have to think about it slightly before you get started into our equilibrium process. Really, the first thing that I want you to do is start by thinking about all species that are in the beaker. What are all the chemical compounds that we have? Think about the dissociation of the compounds. Remember, ammonium chloride is not ammonium chloride. Ammonium chloride is ammonium ion and the chloride ion, and they're completely separate. So think about dissociation. Don't see compounds as compounds anymore necessarily. Think about how they're going to dissociate in water. Then when you've essentially made a list of what things you have in solution, you're not writing any reactions yet, you're just literally making a list. Hey, what's in this beaker? What is everything that I have in this beaker? Then you're going to use our equilibrium method. You're going to write a reaction, you're going to fill out a nice chart as best you can, you're going to plug into the equilibrium expression and solve. Remember, that is our fallback. You don't know what to do in an equilibrium problem, I guarantee you're going to do that. Guaranteed. The difference with this type of problem and the previous equilibrium problems we've done is that is basically right here, and it's not a huge difference at all. You need to include your common ion concentration in the equilibrium expression. Like if it tells you that we're starting with, like in that problem we saw, 0.1 molar ammonium ion, then you would not put in 0 for the ammonium ion concentration because you know you have 0.1 molar of it. You know you have that. Now, this is something that I see students make mistakes with frequently. Don't be tempted to double a concentration because it's a ratio of 1 to 2 in solution. Like if it tells you, in the example that I have right here, if it tells you that the problem is like 0.1 molar chloride, but let's say in the example reaction that you had to write, you would write 2Cl minus. That does not mean that you have 0.2 molar chloride. No, the problem tells you, it literally tells you have 0.1 molar chloride. Yes, you need 2 of them in the balanced equation, but the problem tells you if you have 0.1 molar, so keep it as 0.1 molar. Don't go randomly doubling it because you don't have it doubled. You have 0.1 molar chloride. Okay, great. I'm really happy that you have 2 of them, but if it says it's 0.1 molar in the chloride ion, then keep it as 0.1 molar in the chloride ion. In terms of writing reactions, because that's always something you want to be cognizant of, you're writing the exact same reactions as you would before. The common ion problem, you are not in any way changing the reactions you're writing, meaning if the problem gives you a Ka value, you write a Ka dissociation reaction. If it gives you a Kb value, you write a Kb reaction. If it gives you a KSP value, you write a KSP reaction. So we are very much using our same process. We just are not necessarily starting with 0 product anymore. So sample problem, calculate the molar solubility of solid calcium fluoride, and gives us a KSP value, that's important, in a 0.025 molar sodium fluoride solution. So the first thing that we want to do is think about everything that we have in solution here. So we have CaF2 solid. We know that. And from that, we're going to get a little bit of the calcium ion, right? Not a lot at all because it's insoluble, so it's only going to dissociate a little bit. And we're also going to get the fluoride ion. So I'm not really writing a reaction, I'm just kind of thinking, well, okay, if I've got solid calcium fluoride, then it's going to dissociate a little bit. I'm going to get calcium ion and fluoride ion. So that sort of takes care of that's in the beaker. But then it also says in the beaker that we have 0.025 molar sodium fluoride. Now, sodium fluoride, this is soluble salt. So that means it dissociates 100%. So that means that I don't have NaF anymore. What I do have I have some Na plus. I'm going to have 0.025 molar Na plus, right, because it dissociates into a 1-to-1. And I also have 0.025 molar F minus. Now, the reason I'm making this list is that I can see what is the common ion here. Well, the common ion, I think if we make the list, becomes pretty apparent because I'm going to have fluoride from the calcium fluoride dissociation, and I'm also going to have fluoride from the sodium fluoride being put into this solution. So the fluoride in this case is the common ion. And by making this list right here, I have very clearly identified that that is exactly how much fluoride I have. So now that I've done that, I'm going to start with our equilibrium method. I'm going to write a reaction. I'm going to fill out an ice chart. I'm going to plug into the ice chart and solve for whatever it's asking me for. So first up, the reaction. Well, what reaction to write? That's always the big question, right? Okay, they gave me KSP. They gave me KSP of CaF2. I'm going to write that reaction. I'm going to write the reaction for the equilibrium constant that they gave me. So I'm going to write the reaction for calcium fluoride dissociating to calcium ions and fluoride ions. That's the reaction that this KSP value describes. Great, so now I'm going to fill in the ice chart, ICE. Well, this is a solid, so I don't need to fill out anything for that because we don't have concentrations for solids. I'm not starting with any calcium ions in solution, but I am starting with 0.025 molar fluoride, right? Because right here it says I'm starting with 0.025 molar fluoride from the sodium fluoride. And here's an example where you're not going to randomly double this into 0.05 molar fluoride because it says right here 0.025 molar fluoride. That's how much fluoride we're starting with. Yes, it's very nice that it has a coefficient of 2, but that's not going to impact, it's not going to change the fact that you're still starting with 0.025 molar fluoride. So change. So I don't know equilibrium concentrations, so my change is going to be X. So it's going to be plus X for the calcium, and it's going to be plus 2X for the fluoride. So the equilibrium concentrations, calcium is going to be X, and fluoride is going to be 0.025 molar plus 2x, which I'm going to make my assumption, because the K value is very small, right there, is approximately 0.025 molar. Now you're like, but it's 2x, so can you still make that assumption? If you doubled Mrs. Julian's salary and then subtracted it away from Bill Gates' salary or added it on to Bill Gates' salary, he still wouldn't notice, right? If you double something that is incredibly small, it's still very, very, very small. So yeah, it's 2x, that's nice, but we can still make this assumption. We can still assume that x is going to be very small. Great, we have filled in the ice chart, so now we're going to go to the equilibrium expression, and I am just going to erase this a little bit because I'm starting to run out of room. So the KSP expression, KSP is equal to the calcium concentration times the F minus concentration squared, and plugging in values, 4 times 10 to the minus 11th, and then from our ice chart, calcium was X, fluoride was 0.025 molar, but you have to square it, and then we're just going to solve. So I mean, at this point it's pretty easy, right? So I solve and I get 6.4 times 10 to the minus 8th molar. And that, from our ice chart, is equal to the calcium ion concentration. But I read what the problem wants. It wants the molar solubility of solid calcium fluoride. Now remember, molar solubility means molarity. Okay, good, we have molarity, but right now we have molarity of the calcium ion. But I can say that that is equal to the molar solubility of calcium fluoride because the calcium fluoride is a 1-to-1 ratio with the calcium ion. Right, the molarity of the calcium is that value, so therefore, because it's 1-to-1 with CaF2, the molar solubility of the CaF2 must be the same value. So again, that's just getting it back from the concentration of the ion to the molar solubility of the solid. Now we do want to check our assumption. So we had 2x, so I'm going to do 2 times 6.4 times 10 to the 8th, so 2 of our x's. We assume that 2x, when added to 0.025, would still be 0.025, so I'm going to divide by 0.025 and then times 100. I mean, x is tiny. This is an absolutely, absolutely tiny value. So I get 5.12 times 10 to the minus 4th percent, which is definitely less than 5, so we are good. So that's a common ion problem. I hope you see that this is incredibly similar to our other equilibrium problems so far. We're really just starting with some initial product, but that's it. You're doing literally the exact same process. So what's different if you have a Ka or Kb problem, etc., etc.? I do want you to make a list of species. Think about that dissociation of compounds. Think about what ions a soluble compound will split into in water. Think about what ions you have. With both Ka and Kb, the problem is usually asking for pH. X is going to be H plus concentration or hydroxide concentration. So, solve for X and then do your pH calculations as needed. Now, typically in Ka and Kb problems, because I did a KSP problem, you're usually going to be making two assumptions, one for the reactant and one for the product. With KSP, I didn't have to make an assumption for the reactant because the reactant was a solid, so it wasn't a part of the equilibrium expression. But if you are doing it with Ka or Kb, then you are making an assumption on two ends. You don't have to check twice, you only need to check once. If you check X against your smaller concentration and it's less than 5%, then you know for sure that X is going to be less than 5% of the larger concentration. So just, look at your numbers and check X against your smaller, and if that works out, then you don't need to check the larger and it'll be fine. And as always, what reaction do you write? Write the dissociation reaction that describes the K value. Let the K value be your guide to the reaction if you have not been supplied one. So that's the common ion problem, and tomorrow you will be doing example problems with common ions in the different types of equilibrium problems, and hopefully getting used to this idea of cutting down the percent dissociation.